This training video has been prepared for automotive mechanics who are trained in the repair and servicing of automotive vehicles and the use of related tools and equipment. The information contained in this training video is general in nature and does not contain specific advice or repair instructions. We recommend that automotive vehicle repairs are carried out by a properly trained and qualified technician and in accordance with the manufacturer's instructions. When working on automotive vehicles, always use appropriate safety equipment and procedures. Welcome to Autotech's training video for Common Rail Diesel Advanced System Diagnostics. Along with this video, you'll have received a technical training manual, which we'll refer to throughout the video. On the back of the manual, you'll find more of our training material available from Autotech by calling the number 1300 300 352 or by contacting your Repco account manager. During this video, we'll cover off a basic introduction to Common Rail Diesel technology, the main components you're likely to see on a CRD engine, CRD future technology. We'll step through the diagnosis process of 5 practical examples, and we'll recap everything we've learned in a conclusion. So why are diesels still such a popular choice of engine? After all, diesel's well renowned for being dirty, smelly and noisy in operation. Well, diesel has approximately the same carbon content as unleaded petrol, but diesel is 12% more dense, and when coupled with a higher compression engine and a few other factors, this makes a diesel engine up to 40% more efficient than its unleaded counterpart. These efficiencies, coupled with the use of exhaust after-treatment devices, mean that CRD can be up to 20% lower in exhaust emissions per kilometre when compared with an unleaded engine. So why Common Rail Diesel then? It's simple. Common Rail control systems make the diesel exhaust emissions cleaner and maximise the performance. It can do this because of much higher fuel pressure, which produces better fuel atomisation. This means the fuel is more volatile, or, in other words, it burns easier. Electronic injector control allows precise injection quantity and timing, and the ability to inject multiple times per combustion stroke. Using exhaust after-treatments, such as the diesel particulate filter and exhaust fluids, means that emission levels are greatly reduced. In this video, we'll look at each of the components that CRD uses to allow these benefits, looking specifically at each component's design and function, as well as some common diagnostic tests. So let's take a look at each of the 4 different phases of combustion in a diesel engine. The names of the combustion phases have been used ever since mechanical diesel injection systems were invented. Now, CRD combustion effects are very different, however, we still use the same terms. In this section, we use a graph to describe each of the phases of combustion. The vertical axis on the graph indicates cylinder pressure. The horizontal axis indicates crankshaft rotation or time. The dotted line in the centre of each graph indicates piston top dead centre. The dotted blue line indicates native cylinder pressure. Native cylinder pressure is the pressure generated by piston movement without fuel. The coloured section represents combustion pressure and temperature once the fuel is injected. Here, we're going to compare the combustion phases from that of a mechanical injection system on the left to a common rail system on the right. The graph on the left shows where the delay period occurs during the start of injection. This is caused by a combination of low cylinder temperature, too much fuel delivered at the same time, and poor fuel atomisation. The graph on the right shows how a common rail system delivers less fuel initially, which, at higher pressure, achieves better atomisation and a far more combustible mixture. This results in very little delay period under the same conditions. Uncontrolled burning occurs when the temperature generated by compression finally ignites the fuel mixture, as shown on the left. The result is a sudden surge in cylinder pressure, resulting in the sound we know as diesel knock. With a CRD system, a second pre-injection continues the gradual increase of cylinder pressure and temperature. This gradual pressure rise is the reason why a CRD is much quieter than the older mechanical injection systems. In the controlled burning phase, the injector is still open, and fuel is now being burnt at the same rate as it's injected. It's at this point where maximum torque is generated. In the CRD engine, the injector opens for its main injection just a few degrees before top dead centre. The exact amount of fuel required is injected, meaning no wastage, and cylinder pressure and temperature continues to change gradually. This is the final phase, called afterburning. In the mechanical injection system, the injection has stopped and cylinder pressure plummets. These conditions mean that combustion is no longer effective, and any unburnt or partially burnt fuel is eventually released into the atmosphere as smoke, soot, and other noxious gases. In the CRD system, a post-injection adds a small amount of fresh fuel, increasing the temperature of the afterburn phase and making it far more efficient at burning off the remnants. A second post-injection can be used in systems that use a diesel particulate filter, or DPF. The second post-injection occurs after all combustion has ceased. The unburnt fuel travels down the exhaust until it enters the DPF, where it burns at the extremely high temperatures needed for DPF regeneration. To put all of those different phases into perspective, all four of these phases happen in less than 8 milliseconds. At 2,000 revs per minute, that's up to 85 injections per second. And that's just one injector. It takes about 300 milliseconds for a human to blink, so that just goes to show how precise the operation of the engine management system needs to be. Now let's take a look at the components of the CRD system. As all manufacturers have their own design differences, I'll show you the components of a generic CRD system. All of the components that you're likely to find on most CRD engines. First of all, we have the transfer pump. This transfers fuel from the fuel tank up to the high-pressure fuel pump. The high-pressure fuel pump is also known as the delivery pump. On the high-pressure pump, we can see the fuel metering valve and the fuel temperature sensor. Sometimes this temperature sensor can be found elsewhere in the engine bay. This is the fuel rail, also known as the common rail. The fuel pressure sensor is usually found here, and on newer CRD systems, a fuel rail pressure regulator which works in conjunction with the fuel metering valve in the pump to maintain fuel pressure. Think of it this way. The fuel metering valve allows fuel into the rail to raise pressure, and the fuel rail regulator releases fuel back to the tank to lower the pressure. This dual setup allows much better fuel pressure control. The fuel rail distributes the fuel off to the injectors. On the return side of the fuel system, you can see here we have a check valve. This valve is rarely a component on its own and is normally located within the fuel return pipe as part of a union or a T-piece. The purpose of the check valve is to hold a small amount of back pressure in the fuel return system, helping the injectors close quickly. Last but not least, we have the powertrain control module that controls all of these parts. To connect all of these components together, first is the low-pressure supply line. Then, the high-pressure fuel lines. And fuel return lines from the injectors, rail pressure regulator and the high-pressure fuel pump, back into the fuel tank. And of course, electrical wiring from the control module. Let's take a closer look at each of these components. There are 3 different ways of getting fuel from the fuel tank to the high-pressure fuel pump. Listed here are the different ways in order of popularity. Most high-pressure pumps incorporate a mechanically driven transfer pump which draws fuel into the high-pressure fuel pump. Some CRD systems use an electrical pump in the fuel tank to supply the transfer pump. These systems are usually self-bleeding or may require a valve to be manually opened to release the air. The fuel pressure from these pumps can vary anywhere between 50 and 400 kilopascals. But remember, just because this is classed as low pressure doesn't mean it's not dangerous. Some systems use an electrical pump in the tank and a second intermediate electrical pump to supply fuel to the high-pressure fuel pump instead of a mechanically driven pump. The pressure is stepped up incrementally as it passes through each electric pump. This setup is typically found on Volkswagen and Audi CRD systems. This is a typical in-tank electric pump. You can also see the fuel level sender here too. Here are two different types of mechanical transfer pumps: a gear-type pump and a trochoidal type. You can usually tell by looking at the shape of the housing as to what sort of mechanical pump is fitted. And an inline electrical fuel pump. The next component to take a look at is the fuel metering valve. There are lots of names used by different manufacturers for the fuel metering valve. You can find a list of them in your book on page 14. The fuel metering valve is usually located on the inlet side of the high-pressure fuel pump. The PCM uses duty cycle control of this solenoid to limit the amount of fuel entering the pump. This, in turn, controls the pressure of the fuel in the fuel rail and injectors. There are two methods that manufacturers use to control fuel rail pressure: single pressure control and dual pressure control. Single pressure control systems use only the fuel metering valve on the pump to control the pressure in the rail. Dual pressure control systems use the same fuel metering valve as the primary pressure regulator, but also employ a second pressure regulator in the fuel rail to help fine-tune the pressure. It's important that you know which system you're working on when conducting fuel system diagnosis. The high-pressure fuel pump is mechanically driven by the timing belt, timing chain, or timing gears. In most applications, this pump is capable of producing pressures of 140 to 200,000 kilopascals. That's 20 to 30,000 psi in the old language. In some systems, pressures can reach as high as 70,000 psi. Here we have a cutaway version of a 2008 Suzuki Grand Vitara high-pressure fuel pump. On the end of the pump closest to us, the mechanical transfer pump can be seen. There are also 3 small pistons which create the high pressure required for injection. The fuel metering valve can be seen in the top left of the picture. It's interesting to note that high-pressure fuel pumps on early common rail diesel vehicles weren't timed to the engine. However, the later ones are. It's worth checking this information before you start removing a pump on a CRD engine. Looking a bit more closely inside this pump, you can see each of the components and how they work together. In this video, you can see each of the parts moving together. It's important to remember that all of the moving parts inside this pump are lubricated by the diesel fuel. If the fuel supply is restricted or lost, damage will occur to the highly stressed bearing and cam surfaces. This next video shows a close-up of how the high-pressure fuel is developed. The fuel enters from the right past the check valve, and high pressure is created above the piston. It then continues to the left, out of screen, into the common rail. This high-pressure pump has a different design to what we've just looked at. This type can be found in Volkswagen models. It uses a 2-lobe cam acting on one piston to create the high pressure. The fuel enters from the pipe on the lower right-hand side, then travels through the fuel metering valve to the top of the piston and then into the fuel rail. The low-pressure transfer pump will deliver more fuel than this high-pressure pump requires. So the small blue check valve on the lower right allows excess fuel to be returned to the fuel tank. This way, there's a constant flow of fresh fuel to lubricate the pump. Apart from storing high-pressure fuel ready for injection, an important role of the fuel rail is to dampen any pressure pulses created by either the high-pressure fuel pump or the injector valves opening and closing. Timing the fuel pump to the engine is one way that manufacturers have reduced the effect of these pulses. But the fuel rail also contributes to this by absorbing movement. Fuel injectors are either electrosolenoid or piezoelectric operated. And at the time of filming, all CRD engines sold new contain indirect acting injectors. Indirect acting means all PCM electrical signals act only to open and close valves inside the injector. These valves change fuel flow and pressure inside the injector, which in turn allow the injector needle to open. The electrical signals don't lift or move the needle directly. It's the fuel pressure that forces the needle to open. These injectors can operate at up to 150 volts and have compensation codes that should be programmed into the PCM. We'll talk more about these compensation codes a bit later on in the video. If you turn to page 17 in your training manual, you'll find a picture similar to this, with spaces to complete the missing descriptions. We'll start at the top and work our way down. First one is the PCM switching circuit. This is where the injection signal is generated inside the PCM. This is the fuel return, which is more commonly known as the spill pipe. This is where excess fuel leaks off and goes back to the fuel tank. The electrical solenoid. This is where the injection signal from the PCM turns into a magnetic field. In the centre of the solenoid is the auxiliary spring. This holds the auxiliary valve shut when there's no injection signal. The auxiliary valve is pulled on by the electrical solenoid, opening the pressurised fuel chamber above the needle. The high-pressure fuel enters the injector via the fuel inlet. The injector needle allows fuel to spray out of the injector nozzle. The needle return spring holds the needle closed when not spraying. And at the bottom, the injector nozzle. Now, turn to page 18 and let's look at how this injector works. In your book, you'll see 4 pictures of injectors and descriptions next to them. You'll need to cross out the incorrect options as seen on the screen. In this picture, the injector is closed. The ECM command is off. The auxiliary valve is closed. Fuel pressure behind the needle is equal to that of the rest of the fuel inside the injector. So at this stage, the needle is still. And the injector nozzle is closed. Injector opening. Now the ECM has commanded the injector to open. Auxiliary valve is now open, allowing fuel to escape into the return line. Because the valve is open, pressure behind the needle is lower than it was before. At this moment, the injector needle remains still, as the pressure differential in the injector is not great enough yet. That leaves the injector nozzle closed at this point. The injector is now opening. The ECM command is still on. The auxiliary valve is still open, and the pressure behind the needle has dropped even further. This allows the pressure of the fuel near the tip of the injector to push the needle against spring pressure to open the injector. Now the injector sprays fuel from the nozzle. The injector is closing. The ECM has now switched off the injector, and the auxiliary valve closes, stopping fuel from bleeding off into the return line. At this moment, the pressure behind the needle is now starting to increase again from the reserve fuel in the common rail. With the aid of the spring, the needle starts to close. Solenoid fuel injectors were mostly used in early common rail diesel systems. Their relatively slow response time means they are only useful for 2 or 3 injections per cycle. Due to tightening emission laws, manufacturers are now using piezo injectors for more accurate injection quantities. A piezo injector works in a similar way to a solenoid type. The only difference being that a piezo crystal is used to create movement instead. Piezo crystal is man-made, usually quartz, and has a special characteristic. These crystals increase in size when they receive a pulse of current. It's the expansion of these crystals that operates the auxiliary valve in the injector. Piezo injectors are able to operate up to 6 times per cycle. This is due to having less moving mass inside the injector. A faster response time means less wasted fuel and less tailpipe emissions. On the screen is a list of inputs and outputs you might expect to find in a CRD control system. Most of these are similar to that of a petrol EFI system. You can find this list on page 27 of your manual. The exhaust system is where manufacturers have recently made some of their biggest gains in reducing emissions. There's a cost to this though, so manufacturers have to find a delicate balance between fuel efficiency, power output, exhaust emissions, and of course cost. Those emissions that make it past the exhaust valve must be treated in the exhaust system. These treatments are known as diesel exhaust after treatment. In this Mercedes exhaust system, the gases pass through the two-way oxidizing catalytic converter, which deals with the hydrocarbons and the carbon monoxide. This chemical reaction increases the exhaust gas temperature to a level where the DPF will work properly. As soot-rich gases filter through the DPF, they leave behind particulate matter. Nitrogen oxide gas continues on to where diesel exhaust fluid, seen here as AdBlue, is injected into the exhaust stream. These mix together and go through a chemical reaction inside the selective catalytic converter, producing nitrogen and water, both harmless chemicals. The exhaust shown here is used on the smaller engines of the Volkswagen Audi group, such as the 2-litre TDI. Instead of using exhaust fluid, this exhaust system has catalytic converters that are impregnated with a chemical that neutralises both the oxides of nitrogen and the hydrogen sulfide gas that remains after combustion. So, how does a DPF work? Once the hydrocarbons and carbon monoxide are dealt with by the oxidation catalyst, the soot or particulate matter is collected in the DPF. Extra fuel injected in the exhaust stroke heats the DPF to a temperature of between 650 and 800 degrees centigrade. This starts the regeneration process inside the DPF, where the particulate matter is converted to minute ash particles. This remaining ash collects inside the DPF until its usable service life has been reached. A question we're often asked is, can you empty the ash from the DPF once it's full? The simple answer is no. Once the DPF is full of ash, it's a throwaway item. Many heavy vehicles have removable DPFs that can be cleaned and reused. But at this stage in time, it's not possible to clean the DPF in a light vehicle. Let's move on to some future CRD technology. Earlier, I explained how an indirect operating injector works by moving a valve inside the injector rather than the needle itself. It's expected that manufacturers will soon start using direct-acting injectors. That is, the piezo element is connected directly to the injector needle. This will ensure that fuel quantity and injection timing are even more precise than they are today, resulting in less fuel wastage and less tailpipe emissions. Cylinder compression sensors are already being used on Volkswagens in the United States, but are not currently used in the Australian market. This sensor is a part of the glow plug, where the glow rod section is able to move in and out with changing cylinder pressure. Sensitive electronics inside the sensor relay a signal to the PCM, where injection timing and fuel quantity are adjusted depending on cylinder conditions. When we start to see these in Australia, it's important to remember that these are a single-use item and must be replaced once you remove them. DPF systems rely on measuring the difference in exhaust pressure on either side of the DPF to measure the contamination level. However, if the filter element was to crumble or degrade, These pressure measurements would no longer be accurate, and harmful gases might be released untreated. To combat this, manufacturers have developed a particulate matter sensor or soot sensor. This sensor is located after the DPF and draws a sample of gas from the exhaust. Soot is deposited on the sensor's element, and a DTC is logged if soot is measured over a predetermined limit. The sensor regularly goes through a self-regeneration burn-off to get rid of the soot from the sensing element. Now that we've seen what components make up a CRD system, let's have a look at some diagnostic examples. Over the next few minutes, we'll take a look at 5 practical examples of problems that we've seen in the real world and show you the steps we took to diagnose and repair each condition. As we go through each of our diagnostic examples, we'll be following Autotech's diagnostic process called logical flow. You'll find this in your training manual on page 33. Logical flow is split into 5 main sections. Information from the customer refers to gathering as much detail about the customer's complaint as possible. This means talking to the customer about when the complaint happens, what it sounds or feels like, and test driving the vehicle with the customer if necessary. Basic inspection means conducting the easy checks. Depending on the customer's complaint, this might mean checking the battery or charging voltage, or visually inspecting a suspect component. You might plug your scan tool in and check for diagnostic trouble codes. Any clues you find here might help shorten the time spent diagnosing the problem. A detailed inspection means digging a bit deeper into the fault to find the cause of the problem. You might want to read up on the component or system to help you carry out further testing. Make sure you use the correct specifications and record the results of your tests. Retest if necessary, as any mistakes made here can prove costly later on. Once you've confirmed the cause of the complaint, carry out your repair. After the repair is complete, it's time to confirm that your repair has been effective. Delete any DTCs logged. Test drive the vehicle if necessary. But, more importantly, try to reproduce the conditions under which the complaint was originally felt. You might need the customer to help you. Let's take a look at our first example of EGR and intake system contamination. This type of intake manifold contamination is caused mainly by exhaust gas particulate or soot buildup on intake system components after it's been recirculated through the EGR valve. Poor quality Australian fuel has in the past been blamed for this condition. However, complaints found on international automotive forums proves this to be a global problem. This example shows a very hard, crusty buildup. However, all vehicles will present differently. This Nissan Navara D22 engine is an example of a much wetter buildup. This is much easier to clean than what we just saw. And a severely blocked EGR valve from a Jeep. Here is a light-hearted example of how not to remove carbon buildup. The victim of this procedure was a Volkswagen TDI.
Check around that outlet. Make sure that outlet that's getting all the flame isn't getting particularly bad.
Once again, this is only a bit of light-hearted comedy. Autotech do not condone or recommend this repair procedure. The only way to remove all the buildup is to remove the component for cleaning, soaking in a chemical bath if necessary, or replacing it with new parts. Some fuel additives claim to prevent this buildup. However, the most successful systems appear to be on-car cleaners, If you use an on-car system, you might want to think about where the carbon remnants go after they've been removed. What sort of damage could be caused by loose carbon chunks in the engine? The first car we'll look at is a Mitsubishi Pajero and Triton fitted with a 4M41 3.2 litre engine. The customer might complain of any one of these issues. Slight to severe hesitation during takeoff or acceleration, usually between 1400 and 1800 RPM, or poor fuel economy. If it's really bad, the check engine light might also be on. For the basic inspection, we checked for any DTCs, and a map sensor performance code was stored. The next step was to remove the map sensor hose from the intake manifold and check to see if the port is restricted. Using a bore scope, the technician was able to have a look inside the inlet manifold, and as you can see, there was quite a build-up of carbon. The next step to take was to start dismantling the engine to gain access and get a better view. And as you can see, the inlet manifold has lots of carbon build-up. The manifold was so heavily contaminated that the inlet manifold flaps had no chance of working. How many kilometres would you expect this to occur at? 60,000? 100,000? 150,000? We've heard of this happening at the first service, 15,000 Ks. There are many factors that might influence how quickly this happens. Things like driving style, fuel quality, service history, and possibly design flaws with the engine. In this instance, the repair involves removing and cleaning the contamination or fitting a modified manifold from Mitsubishi. Interestingly, this modified manifold won't stop the build-up from occurring and doesn't change the EGR operation. It merely moves the map sensor sample tube upstream of the EGR valve. Contamination will still build up until engine performance is affected. To verify the repair, erase any DTCs in the system. Reproduce the same conditions that caused the fault in the first place. This might be a test drive. Recheck for DTCs and return the vehicle to the customer if the problem has been fixed. So what can we do about this longer term? At the moment, additional maintenance is the key. Just be sure that any fuel tank additives or on-car cleaners are safe for the engine and don't affect any warranties. So how are manufacturers overcoming this problem? It's called low-pressure EGR. This system draws EGR from after the DPF and deposits it in the suction side of the inlet manifold before the turbo. The DPF has cleaned the gases of soot, so there's nothing left to deposit. So, the obvious question is, why not use low-pressure EGR for everything? Well, here's the answer. High-pressure EGR is very efficient at controlling emissions due to the high volume that can be delivered in a short time. But as a consequence, the gas is very sooty and causes contamination. Low-pressure EGR is slow and doesn't suit all driving conditions, but the gas is clean and won't cause any issues in the engine. A small filter can also be used in this EGR system to catch any particles that might damage the turbocharger if the DPF were to degrade and crumble. Now we'll move on to our next example, fuel system bleeding. Whenever a fuel line is removed or disconnected, you should consider whether the system will need bleeding or not. Vehicles with only a mechanical suction pump will, in most cases, need to be manually bled. If you're not sure, check the workshop manual or call Autotech. Here are just a few manufacturers that require bleeding once air has entered the system. Not all models or engines within these brands need bleeding, so it's important to identify which system you're working on. Symptoms that the customer is likely to experience when air's entered the fuel system can range from hard starting, unstable idle, cutting out after a short period, or poor performance. It's difficult to see air in the fuel system. so it's good practice to carry out bleeding whenever the car has run low or run out of fuel, if the filter has been replaced or drained of water, or if any fuel lines have been disconnected. As we all know, customers won't always admit to running out of fuel or to attempted home maintenance, but it can be helpful to your diagnosis, so make sure you ask. Using a bleeding pump, you should slowly pump fuel through the low-pressure system until air bubbles stop appearing or the bleed pump stiffens. Clear hoses on the pump allow you to see air bubbles in the fuel and monitor the bleeding process. Under no circumstances should the high-pressure fuel system need bleeding. Severe injuries can be caused by the high fuel pressures in the system. Once finished, it's important to test the car under the same conditions that the original complaint was made. For example, this might mean driving under heavy load, or keeping the car overnight for a cold start test. Some manufacturers are programming their PCM software to induce an engine misfire or even engine shutdown when the fuel level is low to protect the pump from running dry. After all, diesel is what lubricates the pump. Ford's programming is called run dry protection, and Land Rover Range Rover calls theirs run out of fuel or roof strategy. How does roof strategy work? The vehicle operates normally throughout its tank of fuel, until the low fuel warning lamp illuminates and the range on the dash shows 72 kilometres to empty. At this stage, there are 9.5 litres of fuel in the tank. The distance remaining figure shown above the diagram is the actual distance that the car will travel using the remaining fuel in the tank. The figure that the customer sees on their dash will always be slightly less. As the customer drives further, the range will show 0 kilometres. The tank will have about 4.5 litres left. If the customer chooses to keep driving, the PCM will induce a misfire into the engine as an attempt to get the driver to add fuel. A short distance further, the PCM will shut the engine down, but will enable restart with the misfire. When the tank holds 2 litres or less, the PCM shuts the engine down and prevents starting until fuel has been added. It's not only Land Rover using this system. Ford shared this technology in the territory, Peugeot models, Jaguar and Citroën. To cancel the engine shutdown mode, the customer should add at least 5 litres of fuel, then turn the ignition on for 20 seconds, then off. Repeat steps 2 and 3 2 more times, and the engine will start. Roof strategy works well when the fuel level sender in the tank is working properly and the tank has its original shape. It's always worth checking for damage or dents in the tank that might cause incorrect readings. What should you do when a car's filled with the wrong fuel? It's important that you don't turn the ignition on or start the engine. If it's got an electric transfer pump, the unknown fuel might be pumped throughout the system. The repair really depends on the extent of the contamination. It can be as simple as flushing the tank and replacing the filter, or could mean replacing all the parts in the high-pressure fuel system that could have been damaged. An expensive mistake for any customer. Let's take a closer look at a fuel metering valve malfunction. We looked at this valve earlier in the video. It's the only actuated part of the fuel pump and the only fuel pressure control device, unless there's a second regulator in the fuel rail. It's also one of the parts most prone to failure. In this example, we'll use the Isuzu or Holden 4JJ1 3-litre engine as a reference. The customer is likely to complain of lack of power during takeoff and acceleration, or hard starting, and sometimes the check engine light can be on. Some basic checks start with a visual check of the fuel system, particularly under the car, for body or fuel line damage. This model has a fuel cooler that's virtually unprotected underneath. Check for fault codes in the system, we found 3 DTCs in the PCM, 2 related to the fuel system and 1 unknown code. It's important that you don't disregard any DTCs that don't have a description. This usually means that the scan tool isn't programmed with the information, but it's still a real fault. Autopedia defines this unknown DTC as a fuel rail pressure regulator fault. As there's no other pressure regulator in this system, this points to the fuel metering valve in the high-pressure pump. As mentioned earlier, manufacturers have lots of different names for this valve. The next step is to look at live data on the scan tool. You want to be able to see the desired fuel rail pressure, the actual fuel rail pressure, and the fuel rail pressure regulator command all at once, so you can see what's happening in real time. Live data can be really helpful when it comes to diagnostics. But unless you know what the values should be, they're just numbers on the screen. You'll find this info on page 41 of your book. Here's the data on the scan tool screen. And so it's easier to see, a close-up. With a live scan tool screen, you'll find that these values are difficult to make sense of, especially as they're constantly changing as the engine operates. So to make it easier, use the graph function on your scan tool. Again, here's a close-up. As the RPM is increased, it shows exactly what's happening to fuel pressures. Engine speed rises. Desired fuel pressure rises, but the actual fuel pressure drops. This fuel metering valve is spring-loaded to stay open and gradually closes the more current is commanded from the PCM. This current is measured in duty cycle or percent on time. The higher the commanded percentage, the more closed the valve is and the lower the fuel pressure should be. Here, the PCM is hardly closing the valve at all, in an attempt to raise the fuel pressure. To ensure that plenty of fuel is available to the high-pressure fuel pump, we need to carry out a low-pressure fuel delivery test, which you can find on page 42. Remove the fuel line as shown and measure how much fuel is delivered within a set period of time. Carry out the same test at the fuel tank outlet to eliminate the chance of a pinched or blocked fuel line. In our case, we met the specs, so the next step is to replace the fuel pressure regulator. In this car, the regulator can be replaced without removing the high-pressure fuel pump from the engine. A revised part has been designed to fix this problem. You'll find the part number on page 40 of your book. However, you should always check with the supplier that the part number is correct. Always replace the fuel filter. Bleed the fuel system. And then carry out a relearn for the high-pressure fuel pump. This is a critical step, or else the engine won't run correctly. You'll find this process on page 43. To verify the repair, erase any DTCs and start the engine. You can see from the before and after live data that the new part has fixed the problem. Check for DTCs again and test drive the car. It's important to remember that the car can remain in limp mode if you don't delete DTCs or carry out a fuel pump relearn. The graph on the left shows the car still in limp mode, and the one on the right after clearing DTCs and doing a fuel pump relearn. Let's move on to example number 4. The vast majority of common rail diesel systems require injectors to be coded to the PCM. Normally called compensation coding, these allow the PCM to make adjustments for slight variations in manufacturing tolerances. For example, how tight the injector needle fits in the housing, or minute variations in how powerful the piezo crystal is. At the time of manufacture, the injector is measured and assigned a code so the PCM can make adjustments for these variations. So, why are compensation codes so important? Firstly, the injectors don't have to be made to such extremely accurate specifications. This means that they cost less to make. It also means that the PCM can correct the injection duration for small differences in each injector. This means less exhaust emissions. The compensation code is usually a string of numbers and letters on the top of the injector. Here, you can see that Bosch use 7 digits in their code, whereas Denso use 30. It's not possible to guess or change any of the digits in the code. An incorrect code will show as an error on the scan tool and won't be accepted by the PCM. The injector is flow tested after manufacture, under various pressures and pulse widths, and the difference from specification is what makes up the compensation code. This graph shows how Denso measure the 12 correction points that make up the 30-digit code. We'll do some injector diagnosis and coding in this example using a Toyota 1KD FTV engine. The customer might complain of an excessively noisy or rattling engine. At first, this noise will only be evident during a cold start, but with time will get progressively worse until it rattles continuously. To cover off basics, check for trouble codes in the PCM. If there are any present, get more details and diagnose these before continuing. This vehicle didn't have any DTCs when we checked. To carry out a detailed inspection, the vehicle needs to be parked overnight for a cold start. Before starting the engine, plug in your scan tool and bring these live data values into view on one screen. Engine coolant temperature, fuel pressure, injection feedback or correction amount for each cylinder, and injection volume. Start the engine and compare the values in the scan tool to those in the table. This table is also in your manual on page 49. Here's a close-up of that table showing the expected feedback values for each injector. And here's our scan tool live data. It's pretty clear that there's something wrong with injector 3. All of these values should be between -3 and +3 cubic millimetres or millilitres. Injector 3 shows -8.1, indicating the PCM is trying to reduce the amount of fuel being injected. This injector is delivering too much fuel, and the rattle in the engine is coming from the uncontrolled combustion occurring in the cylinder. Since the PCM doesn't have a DTC for excessive fuel correction, this problem can only be diagnosed by monitoring the live data in the scan tool. Left undiagnosed, this problem could cause severe engine damage. It's even been known for excessive fuel to burn a hole in the piston. So what's the problem with these injectors? The answer to that is sodium carboxylate. This is an acid crystal that builds up inside the injector and causes the needle to seize. Fuel then floods into the engine, causing the rattle. This is the crystal under a microscope. Autotech recommends replacing all injectors if one is faulty, and Toyota state that new injector pipes must be fitted when replacing the injectors. Once fitted, it's time to assign the compensation codes with a scan tool to ensure that the PCM knows that different injectors have been fitted to the engine. Entering the code is usually easy if your scan tool is compatible. These screenshots are on page 48. Choose your vehicle, then select Injector Compensation in the main menu. This screen simply tells you what the function does. This allows you to choose the cylinder you want to code. Then enter the code from the top of your fuel injector. Look carefully, as these numbers can be very small. Confirm the number is correct, and the scan tool will let you know that the coding was successful. Verify the repair by looking at your live data again. The correction value should now be within specifications. And as a last step, make sure there are no DTCs in the vehicle. These fuel injectors were brought into service overseas in July 2000 when the 1KD FTV engine was released. In 2004, a service bulletin was released by Toyota which addressed the cold start knocking problem. In March 2005, the engine was sold in Australia in the Hilux. The engine was revised in 2006 to make it comply with Euro 4 legislation. It was in December 2007 that Toyota released modified injectors that had a revised nozzle to help prevent the acid buildup. These were more resilient than the previous ones but weren't totally immune. In September 2009, the 150 Series Prado was released. These were fitted with a second revision of injector with a diamond-like coating on the needle. They're a huge improvement, and Toyota have also released the improved injector for earlier models. For the Australian market, it's the early Euro 4 engines that are most susceptible to this problem. So what can happen if the injectors are replaced without coating them? Well, the engine should adapt, but it'll take a long time. In the meantime, the engine may be noisy, smoky, and could be damaged due to under or over fueling. You'll also find it difficult to diagnose various problems. We'll move on to the last of our examples. We're going to look at the Volkswagen Golf with the 1.6 litre and 2 litre TDI engines, fitted with a diesel particulate filter. We're going to look a bit deeper into how the DPF regenerates. Firstly, we need to take a look at how the concentration of soot in the exhaust is measured. Manufacturers use a term called grams per litre. This measurement shows how many grams of a certain substance is in a litre of gas. In this case, exhaust gas. The amount of soot in the DPF is measured using two differential pressure sensors. That is, a pressure sensor either side of the DPF that measures the difference in exhaust pressure as the gas passes through the DPF. From this pressure difference, the PCM calculates the amount of soot inside. A DPF is normally considered regenerated when less than 5 grams per litre of particulate matter remain. Between 5 and 20, a passive regeneration will take place. This means the DPF will self-regenerate providing the right conditions are met. Usually, the customer won't detect anything happening. If a passive regeneration doesn't take place and the contamination level increases in the DPF, the PCM will conduct an active regeneration. This involves injecting fuel in the exhaust stroke. At this point, the customer might notice a higher idle speed and a change in the gear shift pattern. If the level of particulate matter continues to increase, the ECM moves into the next stage. A warning light will come on the dashboard, indicating the need for what's called a driver-initiated regeneration. This requires the driver to follow specific driving parameters that can usually be found in the owner's handbook. If the customer ignores this light and contamination increases to between 40 and 45 grams per litre, another 2 warning lights will be illuminated on the dashboard. This means the DPF will need to have a service regeneration conducted using a scan tool. At this point, passive, active, and driver-initiated regenerations are blocked by the PCM because of the risk of damage to the DPF. If the measurement exceeds 45 grams per litre, the DPF is considered unserviceable and the PCM will block all forms of regeneration. This is due to the amount of back pressure in the exhaust system and the risk of causing engine damage in the process. The only way to solve this problem is to replace the DPF. This is where you're likely to see these lights on the dashboard. The vehicle we're going to regenerate is the Mazda 6 with the 2.2 litre MZR engine. In this case, the customer is complaining of an orange DPF lamp flashing on the dashboard. Like we saw before, there are various stages of contamination in the DPF. You can find this table in your training manual on page 52. Particulate matter is shown here as a percentage in grams per litre and as a differential pressure. With this Mazda information put into a graph, It looks like this. Compared to the Volkswagen graph in the inset, you can see how different the DPF capacities can vary from one manufacturer to another. Ask the customer how they drive the vehicle and note it on your job card. Visually inspect the DPF, electrical sensors and wiring for damage. Rubber hoses connecting the pressure sensors can also overheat and melt. As you can see here, our scan tool won't decipher the DTC stored. Using the table in your training manual or software such as Autopedia, it's possible to find out what it means. Comparing the live data in the scan tool to the table on page 52, you can see that the exhaust differential pressure is high. This is caused by a contaminated DPF. Interestingly, the scan tool also shows the distance since the last regeneration being 1,275 kilometres. This kilometre reading shouldn't be used primarily for diagnostics, as soot buildup will depend a lot on driving style, fuel quality, and a few other factors. However, most vehicles will regenerate at least once every 1,000 kilometres or so. Before carrying out a service regeneration with your scan tool, make sure the car is parked in a safe area. By this I mean a lot of heat and gas will be generated by the exhaust. Make sure the car is parked on a surface that won't burn or melt, and make sure there's plenty of ventilation both inside and outside the car. Also, don't forget that tailpipe emissions can also be harmful to your health in an enclosed space. The regeneration we carried out in this example took 37 minutes to complete, but can take up to 60 minutes if DPF contamination is high. For safety reasons, it's best not to leave the car unattended during a regeneration. This scan tool shows the sensor readings both before and after the regeneration has taken place. You can see that most of these values have dropped considerably. The exhaust gas differential pressure has dropped to 0. The particulate matter accumulation is 0, and the distance since last regeneration has reset. This indicates that the regeneration has been a success. To verify the repair, erase any DTCs in the PCM and confirm that the vehicle drives normally. It's also worth talking to your customer about their driving habits and making sure they understand the driving requirements to carry out passive and active regenerations. In most cases, the manufacturer will require the engine oil and filter to be replaced after a service regeneration. This is because some of the extra fuel injected will find its way into the sump. Some manufacturers also require the oil to be replaced before the regeneration, especially if the oil is past 80% of its service life. It's possible that the poor oil quality will cause engine damage. Mazda have started placing a sticker next to the oil filler cap to show the limit of oil dilution, indicating the need to change the oil. This is a brochure sent by Mazda to registered owners of vehicles fitted with MZR CD engines. It was in response to concerns caused by excessive oil dilution. But how often do customers really check their oil? Are your customers checking their oil weekly, as most owners' handbooks recommend? Throughout this video, we've looked at why common rail diesel is an important step in emission control, benefits of CRD phase by phase, the key components of a CRD system, the different types of diesel exhaust after-treatments. We saw a couple of new components that we're likely to see in the future, and we stepped through the diagnostic processes of EGR contamination, fuel system bleeding, fuel metering valve diagnosis, fuel injector coding, and a DPF service regeneration. If you have any unanswered questions from anything you've seen in this video, please call our technical department on 1300 300 352, and they'll be more than happy to talk to you. Thank you for watching, and look out for the next Autotech training video.
Not so long ago, cars were pretty easy to fix and everything you needed was right there in your toolbox. These days, cars are more like computers on wheels, and having the right information is the most important tool of all. But where do you go to find this technical information? Do you spend hours on Google looking for answers? Or maybe you call a mate, assuming he knows what he's doing, spending countless hours that can't be billed and losing customers as you try to fix the problems time and time again. As cars become more complex and manufacturers publish more and more technical data, how are you going to keep up? Introducing Repco Autopedia, the ultimate resource for technical information that gives you more know-how for more cars. With extensive wiring diagrams, thousands of OEM-style diagnostic flowcharts, comprehensive component location images, and all backed up by our technical help team. Autopedia has over 1 million pages of technical information covering 52 vehicle manufacturers, all accessible via the easy-to-use website. Now let's see Autopedia in action. Using the example of a Volvo S40, 2008 model, fitted with the 2.4-litre engine. Let's get some information for the electric sunroof circuit by simply clicking on the wiring diagrams icon and selecting the sunroof diagram from the available list. Like all Autopedia content, these diagrams can be printed for use at the vehicle. Now let's see how Autopedia can help you sort out trouble code problems. Troubleshooting diagnostic trouble codes is as simple as clicking on the Diagnostic Trouble Codes icon and selecting the relevant code from the available list. These OEM diagnostic flowcharts are the same information that dealerships use to guide them step by step through diagnosing the problem. If there's no information available on Autopedia, the category will be greyed out. No problem. Simply click on the greyed out icon and a Tech Help request form is generated.
Just got your priority help email, and I want you to confirm it's the 2008 model. Okay, fine. I'll be sending that information to you in a few minutes.
Well, gone are the days of your points and plugs and things coming in for a quick tune-up. Now everything is very electronic based. Almost have to be a computer technician rather than just a mechanic. Got a car that's got an electrical problem, we need to be able to first diagnose it with our tools, etc. Then we need the information on hand. That way we can actually work through a process to find out what the problem is and resolve it. The biggest thing we find is we can actually get the job done a lot faster, okay, because the information's here. I'm not faxing for information, I'm not ringing people trying to get a bit of a favour, can you send me some information on this? It's all held within the program. It means our diagnosis time is much faster, everything's on hand, we get the job done and car back straight away to the customer. Saves a heap of time, in turn a heap of money. Thoroughly recommended. The process just works from start to finish. Fantastic.
With Repco Autopedia, you have access to the OEM quality data you need to diagnose and complete repairs quickly, meaning you fix it right the first time. For immediate access to your 30-day trial, go to autopedia.net.au and hit the Register Now button. Repco Autopedia. More know-how for more cars.